Hi, my name is David Tudor. I'm a mathematician. I've been doing disease modeling in medicine for about 45 years now. I did a video the other day in mathematical modeling the outbreak of coronavirus. And today I would like to say something else. I've been hearing a lot about testing for coronavirus, testing positive, and how important it is for everyone to run out and be tested, or everyone to be tested who wants to be. But there are a few facts that we should know about results of diagnostic tests, and I would like to try to explain that today in this video. There are some mathematics, but it's, I hope, not too taxing. So we will talk about probability. So the big question is, if you test positive for a coronavirus, or if, for that matter, if you test positive for any diagnostic test, what is the probability that you actually have the disease? So in order to do that, we need to know just a few facts about probability. Here, the conditional probability is a calculation of probability when you know something. So the probability of A, we say given B. So if B is some additional information that I have, I calculate A in the light of knowing B. So the way, I'll let the cat out of the bag right now, the B is going to be that our test is positive, and the A is going to be that we actually have the disease. So what is the probability if you have the disease if you tested positive? The calculation for this conditional probability here on the left, this is a definition, is the probability of A and B. The intersect sign we read as the word and. So that's the probability of A and B divided by the probability of B. So it often happens when we have these conditional probabilities that, as quite often happens in mathematics, things go the opposite way around from the way that you want them. So we need to turn the A and the B around in the other sense. So in order to do that, we use a theorem called Bayes' theorem that says if I have my conditional probability in the one sense, then I can turn it around in the other sense. I can use the probability of B given A. I just have to multiply by the probability of A divided by the probability of B. So there are tremendous lots of other things that we could learn about or explore using conditional probability and Bayes' theorem, but I think this is all we need for today to get at the essential of diagnostic testing that we want to look at. Now, suppose we have a test and we take the test. We're going to actually try to calculate the probability that we did before. There's one more number that we need, is the actual percentage of the population that has the disease. And I'm going to call that P of D, probability of D. Here in this case, I'm going to use that to be a fraction. So it's the probability of a random person selected from your population actually having the disease, or the percentage written as a fraction of the population that actually has the disease. Some epidemiologists would call that prevalence, or some form of it. The next thing we need to know is what the sensitivity and specificity of the test is. The sensitivity is the rate of true positives. That is to say, if you have the disease, you'll be tested positive. And the specificity is the test specific to that disease. That is to say, if you don't have the disease, will you test negative? So sensitivity and specificity are characteristics of a test that anyone developing the test should think about and should test and try to estimate before they start doing the test, and you'll see why in just a few minutes. So now the question in red, I get tested for a disease and the result is positive. What is the probability that I actually have the disease? So in probabilistic notation, what we did before, the sensitivity is the probability that the test is positive given that we have the disease. Little d here I'm using as the disease. So given that you have the disease, what's the probability that the test is positive? The specificity, given that you don't have the disease, what is the probability that the test is negative? So that's another mathematical form of specificity, and then the prevalence is the probability of having the disease in the entire population. So, and that should be estimated from epidemiological data that you have. Now, what we want to do, this mathematical formulation of our question is, what is the probability of having the disease given that you've tested positive? So this is actually the value that we want to calculate today. Going down here and noticing that what we're trying to do is calculate the probability of D given plus, but what we have in terms of sensitivity and specificity are the probabilities of plus and minus giving D or not D. So in fact, we want to turn, in order to calculate the probability of disease given positive, we want to turn that around in terms of the others, in terms of sensitivity and specificity. So we use Bayes' theorem that I spoke of before. And this, for equation 1 here, I've simply taken, it looks nasty, but I've taken the question on the left that we're asked, what's the probability that I have the disease given that my test is positive? And I've turned that around by Bayes' theorem, so it's the probability that I test positive if I have the disease, multiplied times the probability of having the disease in the population, divided by the probability of plus. So already we see that probability of plus given you have the disease is the sensitivity, and the probability of disease in the population is the prevalence. So we've got two parts of our formula there. We simply have to now calculate what the probability of plus is. So we use some mathematics here. I apologize for that, but we can't get around it. If you're positive, the probability of plus is either, you can break it down into two disjoint happenings. Either there's plus and you have the disease, or there's plus and you don't have the disease. Okay, so that seems logical that either you have the disease or you don't have the disease. So they have these two events, and so the probability of plus is going to be the probability of having plus and the disease, or, and here when we do probabilities of disjoint events, we add the probabilities together, probability of plus and not having the disease. So using that then, and we take those intersections, for each of these times we have an intersection. Remember, going back to the definition of conditional probability, we had the probability of an intersection here. So I can actually multiply both sides of this definition by the probability of B, and I have an expression for the probability of intersections. So if I go back down here and look at these two terms here and here, I can actually plug in the definition of conditional probability, and I get this nasty formula here. Remember, that formula was our denominator. That's what we're looking for right here, the denominator of our answer to the question. Okay, so notice here we have the probability of being positive if you don't have the disease, and that's just the opposite event of being negative. So those two events then the probabilities would have to add up to 1. So either I'm positive or negative. So I can replace the probability of being positive by 1 minus the probability of being negative, given that I don't have the disease. And here I have the probability of not having the disease, and that's 1 minus the probability of having the disease. So this has gone by fairly quickly, but now for my denominator, I have everything on the right-hand side is something that I've previously talked about. The probability of plus given D is the sensitivity. This is the prevalence. The probability of being negative if you don't have the disease is the specificity. And there's again P of D. So I can actually make a word equation. Maybe it's a little bit better to understand here. A word equation. I have a test. The result is positive. The probability of being ill after testing positive, this is what we want to do in the first place, is the sensitivity times the prevalence divided by this formula for plus here, the probability of plus, sensitivity times prevalence, plus 1 minus specificity times 1 minus prevalence. So, as usual in my videos, I do a little computer program to show you how to calculate this. So we're going down to R, which is a program that is used to do all kinds of mathematics. Here's my program that I'm doing in R. This is just a review of my definition of words. Sensitivity is the probability of having a positive result if I actually have the disease. The specificity, probability of having a negative result if I don't have the disease. And the prevalence is written here in our case as a percentage of the population who actually has the disease. So those who are developing the test should actually tell you what the sensitivity and specificity are. But let's suppose that there are some high numbers like 0.99 and 0.97 for sensitivity and specificity. A lot of people would think maybe that it's more important for you to detect the disease, so they might attach more importance to sensitivity. But again, this depends on what kinds of scientific questions you're trying to answer. And we don't know, actually 1 in 100, 1% of the population would be extremely large in terms of something like coronavirus. We don't have 1% of the population yet. We hope we never get there. But let's just take that. I've written a function here, as you might recall from my last video about functions. The probability of disease is going to be a function where I can plug in sensitivity, specificity, and prevalence, and I calculate my numerator and denominator and then tell you what the answer is. So I've actually programmed this in, and I've programmed in default values of 0.99, 0.97, and 0.01. So if you run the probability of disease function without putting anything in, then you'll get that answer. So it'll be the answer to our question. If I do a test that has 99% sensitivity, 97% specificity, and a prevalence in the population of 1%, what is the actual probability that I am ill if my diagnostic test is positive? So let's go down to R again. The name of my function I don't want to type, so I'm going to copy and paste. Probability of disease, I'm going to put that here, and I have to put parentheses, empty parentheses in there, and I see that 25%, I have a 25% probability of being ill if my test is positive. So I had my data that I put into the function are sensitivity, specificity, and prevalence. So let's suppose then that we have a higher level of specificity. What are the effects of these things on the actual probability of being ill? So go back and suppose now that I leave the first blank and I write in 99% as the second blank and I leave the third blank. What happens here is there's no sensitivity that I'm putting in, so it's going to use the default value. I ask it to change the 97% to 99%, and the 1% of the population I'm leaving as the default value. So there I see I have a 50% probability of being ill. So let's suppose then that my sensitivity went all the way up to 1. Now I have a sensitivity of 1. I'm guaranteed if I have the disease that this is going to find it out. I still have just barely over 50% for being ill. So how is it that I can actually increase my probability of being ill based on the diagnostic test? That's what we really want to do. We want to, if we take a test and when it's positive, we want to really count on being ill. Well, the idea is that we actually need more. Remember, we used 1% of the population. Let's say we had 5% of the population. So we've gone up to 5% of the population with a disease instead of 1%. Now I have an 84% probability of being ill if my test is positive. But 5% is an enormous amount of the population. If we have a population of 100 million people, that's 5 million people who have the disease, and we're only talking about the numbers in the thousands currently. So if you reduce this down to say 1 in 1,000, which is still a lot, I only have a 9% probability of being ill if the test is positive. Wait a second, let me interrupt myself here. This was the end of the video, but it seems too pessimistic and depressing to think that you have a diagnostic test, you test positive, and then you only have a 25% chance of having the disease, or only a 9% chance of having the disease. This seems very pessimistic, and why would you want to get tested anyway? And I don't want to encourage anyone not to go out and get tested, but let's look and see how to interpret this. First of all, the only information that we have about you in this particular calculation is that you're one of this population that has a very, very small percentage of people who are actually ill. So chances of you being in that small group are also small, even if you do test positive. So what is this solution? I went back and I want to add a few more ideas in here. The first idea we have out of this is that you don't just go get tested for nothing. You need to have some reason for going to get tested, not just to try to test everybody in the world and use testing kits that someone else might really need. So what kind of other information could you have? I went back and I added some to the class notes here. So a little bit of an explanation of why it is that your probability of being ill is so low when you have only one diagnostic test. So what we're going to do here is we're going to, even though there are not two tests for the coronavirus, there's only one for the moment, or at least one per country, and we don't know how dependable it is anyway. So let's just say that you have your own opinion. Let's suppose that you have other information, like you have runny nose and sore throat, and so you consider yourself to be, from your experience as someone who's had flu or diseases before, to try to interpret your chances of being ill. And so think of yourself, in your opinion, once you start having symptoms, as a diagnostic test. So suppose we have two diagnostic tests, here the coronavirus test and your own opinion, and we want to actually see what is, if I say that I'm only going to declare myself to have the disease if both tests are positive. So what is the probability of being ill if I have test 1 and test 2 positive? The big T means positive test 1 and positive test 2. So we go back again, as we had before, the conditional probability is going the wrong way around. So just as we did before when we tried to calculate the probability of D given just the plus sign, one test positive, we go back and we do exactly the same thing. The first thing we apply here is Bayes' theorem to turn the probability around to the conditional probability. And then already, because this is a probability of intersection of two independent things, one of them will not really influence the other, we can calculate that intersection of events by multiplying those probabilities together. So then once we multiply that out, we see that in the numerator here, this is the numerator right here going down to the division sign, that is the sensitivity of test 1 times the sensitivity of test 2 times the prevalence of the disease. So that's our numerator here of the answer to our question. What's the probability of having the disease if both tests are positive? Now, as we did in the plus before, we're going to have to calculate the probability of the intersection of T1 and T2. This is the same thing as having the plus that we had before. So as we did before, we looked at the plus and we said we could either have the intersection and be diseased, or the intersection and not have the disease. So the probability of this union is the sum of the probabilities, and each of those probabilities I can write as a conditional probability, as we did before. And now, because this is independent events here, we can multiply those together in order to calculate the probability of the intersection. And as we had before, we know for the specificity, we know the probability of or not having a positive result, given that we're not ill. And we used probability of complementary events, that having both of these true is 1 minus the probability of having none of them true. So if I plug that in, and instead of the probability of not having the disease, I write 1 minus the probability of having the disease, I get this fairly complicated formula here. Sorry for the mathematics, but it's inevitable. Let's translate this into a word equation as we did before, and I think that's going to be a little more interesting for us, and a little easier to read. So the denominator that we're looking at is the sensitivity 1 times sensitivity 2 times prevalence plus, and once I use my 1 minus tricks here, 1 minus the specificity 1 times 1 minus specificity 2 times 1 minus the prevalence. So that gives me something that I can look at for my computer program. So let's go back to the computer program, and I wrote this out as a computer program that's going to give me the probability of being ill once I define a positive test to be both test 1 and test 2 to be positive. And I've written this as a function so that we can plug different values in. And so I have these default values. I put in the same 0.01 that we had before in the other test, a 0.99 and 0.97 like we had before in the other test. And for you as a diagnostic test with unknown specificity and sensitivity, I just used 0.8, which is not a great test, but it means that you'll be right 4 out of 5 times. So as you see here in our word formula that we had back in the class notes, the numerator was the product of the sensitivities times the prevalence, and the denominator was the numerator was the first term plus the 1 minus specificities and 1 minus prevalence. So we can put that into the computer program. Let's go to R now. And this was called two tests. Was that the name of it? Let me see just a second. Two tests, yes. And I have 1, 2, 3, 4, 5 things I have to put in. Prevalence, 2 specificities, 2 sensitivities, and 2 specificities. So the sensitivity and specificity for test 1 and for test 2. So if I just run this with the default values, the fact that I do know something, what the probability that I had before that was 25% has gone now up to 60%. So now we can look at other possible values. Suppose I increased my own sensitivity up to 0.9, sensitivity and specificity of my own diagnostic test, my own opinion. There you see I've gone up even further to 75%. So the point here to be made is that if I have a very small number of cases relative to the entire population, then doing a diagnostic test on yourself or having a doctor do it with a test that does not have any other information than you are simply someone out of this population. If the test comes out positive, you're most likely not going to have a really high probability of actually being ill. But if you do have other information that you can put into the model, for example, you have symptoms and you get tested because you have symptoms, and you accept the fact that you're ill if you have both symptoms and a positive test, there you can actually increase your probability, your probability of having the disease once you test positive. So I hope this is clear about testing. Please don't just go out and get tested for no reason, but if you do have some extra information, go and get tested. Thank you. Bye.